All right, so I posted your midterm exam scores, and I added 9 points to everybody's exam. So that's like almost a full letter grade there, and the distribution was quite symmetric. I was surprised. I mean, I don't know. Surprised isn't the right word, but I was just like, oh, this is actually a decent decent test. But yeah, maybe just a touch harder than I'd originally intended. So I adjusted that by kind of adding points to everybody's score. If even after the adjustment, your score wasn't as high as you would have originally liked or something like that, I don't want you to feel bad or feel like you're doing poorly in the class or anything like that. It's just, it's one small test in a class that, again, your grades aren't the most important thing. Your grades don't define who you are. And, if it's any consolation, this exam is only worth 20% of your total final grade. And I want you to be able to kind of measure your performance and achievement based on how much you have learned. Like if you're able to do more today than you were 2 weeks ago or 3 weeks ago, then that's good. That's progress. You're learning things, and that's a great thing. And it doesn't, unfortunately, as far as the school systems go, like we have to have some kind of tests and some kind of evaluation of your learning, and that's always a very difficult thing to achieve. And in our class we do a combination of homework and exams, and anyway, if you want to take a look at your exam, you're welcome to do so during office hours. I keep the exams, but come by during office hours. I'm happy to let you look at your exam. You can ask questions, and I'm happy to answer them. There was a handout. I handed it out earlier, but if you didn't get one, put it on the edge of the seat. So we'll take a look. And that's that. It's happy Friday, everybody! It's week 6 Friday. We've got the Super Bowl this weekend. Apparently, the Bengals are staying on campus or things like that under high security, I guess. And we'll see what happens. Of course, we got to root for LA, and then it's Valentine's Day on Monday. So we'll see you guys on Monday. But anyway, we will continue on looking at double precision floating point. We use 64 bits to store our number, and of those 64 bits, we say 1 is going to be used for the sign, 11 are used for the exponent, and 52 are used for the mantissa. And in order to kind of understand and help us learn about this floating point system, we're going to take a look at this miniature floating point system, where we use a total of 8 bits. We'll use 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. And under this system, basically I think it's a little bit harder to reason about things when you have so many bits. Okay, when you have 64 bits and you can represent some of these big numbers, it's hard for our brains to comprehend. So by using a smaller system, we will start to notice some of the odd behaviors of floating point numbers. Okay, it will become really apparent how odd some of the behaviors of floating point numbers are. And those same odd behaviors happen in the mini floating point, and they happen in the double precision floating point. It's just at double precision, the odd behaviors, kind of happen at a, much grander and smaller scale, and so it's a little bit harder to appreciate. But I think with the mini floating point, we'll notice some of these strange behaviors, and we can do that. Okay, so again, the first bit is the sign bit. We use 0 if it's positive, 1 if it's a negative number. We have 3 bits for the exponent. So with 3 bits, everything being, zeros and ones, we can represent 8 different values. 0, 0, 0 is 0, and the 1, 1, 1 is 7. We can represent 8 different values. We reserve the all zeros and all ones to be special cases, which leave us with 6 numbers that we can represent, 6 unique values. And we say half of those are going to be positive, and then 1 will be 0, and the rest will be negative. So we got a bias of 3. So 6, 1, 1, 0, which is normally 6, becomes 3 for the exponent. 0, 0, 1, which is 1 in decimal, becomes negative 2 after we apply the bias in the exponent. Okay. And then the remaining 4 bits we will plug in as the mantissa, and this will be the values after the binary point. And because it's in scientific notation, the number in front of the dot can't be 0, we can always assume it's going to be a 1. And so it's going to be 1 point something, 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 and we plug in those 4 bits from the mantissa into this position after the dot. The 4 bits used in the mantissa represent the digits that trail the leading 1. Okay, so I was going to have you guys do this, but when I asked the previous class to do it, everyone just kind of stared at it blankly. So we'll go over this, right? So, all right, let's say you had this number, 10101010, right? This is kind of like, what's a binary number, binary solo. What would we get? Okay, so when we do this, we're going to break this up into the sign bit, which is the first digit, the exponent, which is the next 3, and then the last 4, which is the mantissa. Okay, now this number doesn't show up exactly on your handout. Your handout only has positive numbers, but even the one where it doesn't show up exactly doesn't appear. Okay, so let's try this out. Okay. The sign bit is 1, so it's going to be a negative value. The exponent is 0, 1, 0. Okay, 0, 1, 0 for the exponent means in binary, 0, 1, 0 is 2. 0, 1, 0 is 2, right? It's 1 in the 2's place, a 0 in the 1's place, right? So this is the 1's place, it's 0. The next value is the 2's place, and the next value is the 4's place. So this is 2 in binary. With a bias of 3, this is negative 1. So our exponent is going to be whatever it is times 2 to the negative 1, times 2 to the negative 1. The mantissa bits are 1, 0, 1, 0, 1, 0, 1, 0. And if we put a leading 1, it becomes 1.1010. 1.1010. All right? Is that okay? Going from these 8 bits here to at least this spot right here, negative 1.1010 times 2 to the negative 1. I want to make sure that part's okay, the translation. Okay. All right, and so now it's a matter of turning this into a kind of fractions and decimals. So what do we have here? So I'm going to have 1.1010. So 0.1, the 1 is a 1, and over here 0.1 is 1/2. I have nothing in the 4th's place. Oops, somehow I'm zooming in. Oh no. What's going on? Okay, so I have nothing in the quarters place. I have 1 in the 8ths and nothing in the 16ths. So I have 1 plus 1/2 plus 1/8. Okay, so this is basically 1 plus 5/8 or 13/8. And then I'm multiplying it times 2 to the negative 1. 2 to the negative 1 is 1/2. So I've got negative 13/8 times 1/2, and I get negative 13/16. And that translates to 0.8125. 0.8125. Okay. So that's how we go. That's how we get this number here. Okay. Another way we could solve for our answer is we could take our number, negative 1.1010, and we could say, well, I'm multiplying it by 2 to the negative 1. And so I could roll the binary point 1 to the left, right? Because when you multiply by 2 to the negative 1, so I roll this over, and now I get negative 0.11010, and I get 1/2 plus 1/4 plus 1/16. Okay, and this is negative 13/16, same thing, negative 0.8125. Okay, what about this? What if we have all zeros? If we have all zeros, we feel like, okay, that should just be the number 0. But with our current system, without kind of this special case for the exponent being all zeros, if we just use the regular old exponent bias of negative 3, the exponent becomes 0 minus 3, and we get negative 3. And then the mantissa bits being 0, 0, 0, 0, and we assume there's a leading 1, this becomes 1.000. And so this becomes 1.000 times 2 to the negative 3, which is just going to be 1/8, right? And this would represent the number 1/8, and that just doesn't make sense. Okay, so what do we do? Okay, well, we have what's called denormalized mode. We're going to have something called denormalized mode, and it was, you know, it's useful for us to kind of assume that there's always going to be a leading 1. Okay, because in binary you only have 2 digits, 0 or 1. And so if it's not a 0, it's going to be a 1, and most of your numbers, you're going to have something other than 0 in front of the binary point. And so it's a safe assumption to assume it's always going to be 1. But we need to have a way to represent 0. If it's always going to be 1 up there, we don't have a way to represent 0. So we have something called denormalized mode. And what we do is, well, we make an exception. We say if the exponent bits are all 0s, then the digit in front of the mantissa bit is going to be a 0. Okay? If the exponent bits are all 0s, then we're going to change it to denormalized mode. The digit in front of the mantissa bits is going to be 0. Okay? Now, if you do this and you just kind of leave the bias as -3 or whatever it is for everything else, there ends up being a discontinuity in the numbers. You end up getting kind of this gap and a jump in the numbers. And so to kind of prevent that, we have to change our bias to be 1 less than normal. So normally our bias is 3, and we would, you would subtract 3 from the exponent to get the exponent bits to get your actual exponent value. But what we're going to do is, in denormalized mode, we're going to subtract 2. Our bias is going to be 1 less than normal. So in denormalized mode, our exponent bias is going to be 2. In double precision, your bias is normally 1023, and we would change it to 1022. So in this case, we have all 0s. The exponent bits are all 0s, 0, 0, 0, so that's going to mean we're in denormalized mode. Our bias is going to be 1 less than usual, which is -2, which will be -2. And then the mantissa bits are going to be all 0s. And when we're in denormalized mode, the leading digit is 0. So we're going to have 0.000 times 2 to the -2, and this leads us to 0. Okay? And you might feel like, well, why do we even have to mess with the exponent? Because it's all 0s here. Yeah, for the case of all 0s, it didn't really matter. Okay? But in the other numbers, it will. So it does make sense, and I'm going to just have to ask you to trust me and the engineers who came up with this design, that using an exponent bit of -2 is what's going to make sense. Okay, so having all 0s will represent the number 0, and that's kind of the first line in your handout. You can see all 0s translates to 0 there. Okay, the other special exponent case is when you have all 1s. All 1s in the exponent will either have one of two special meanings. Okay, all 1s in the exponent and all 0s in the mantissa means infinity. And you have positive infinity and you have negative infinity. So all 1s in the exponent and all 0s in the mantissa will be infinity, positive or negative infinity. If you have all 1s in the exponent and then something other than all 0s, in the mantissa bits, that becomes not a number. Not a number is inherently a floating point number. Okay, it's a floating point number, but it's nan, and that represents, basically, like if you try to do 0 divided by 0, it's going to result in nan, and that's going to be represented with all 1s in the exponent and something other than all 0s in the mantissa. Okay, what is the smallest non-zero value we can represent? Okay, smallest non-zero value will be all 0s in the exponent, and the mantissa bits will be 0, 0, 0, 1. Okay? And what number is this? Okay? Well, exponent bits are all 0. With a bias of 2, our exponent is 2 to the -2. Okay? The mantissa bits are 0, 0, 0, 1. We're in denormalized mode. So this is going to be 0.0001 times 2 to the negative 2. Okay, 0.0001 is 1/16th, right? The first position is 1/2, the next position is 1/4, the next position is 1/8, and the fourth position would be 1/16th. So I've got 1/16th times 2 to the negative 2, or 1/4, and this would give me 1/64th. And so this would be the smallest non-zero value I can represent. I can't represent anything smaller than 1/64th in this miniature floating point system. I can't represent 1/28th or anything smaller than 1/64th. This is the smallest number I can represent. Okay. What is the next number I can represent? The next smallest, the second smallest value I can represent would be zeros in the exponent, and then the next would be 0, 1, 0, 0, 1, 0. 0, 0, 1, 0. So this would be 0.0010 times 2 to the negative 2. 2 to the negative 2 is 1/4. 0010 is 1/8. 1/8. So 1/8 times 1/4 is 1/32. This is equivalent to 2/64ths. 2/64ths. Okay. So we counted from 1/64th to 2/64ths. Okay. So we're incrementing our values from 1/64th to 2/64ths. Okay. And if I keep going, then we'll get 3/64ths, and this would be 4/64ths. This would be 5/64ths. 110 would be 6/64ths. Okay, and we're still in denormalized mode, and we're counting up basically by 64ths. Okay. We can keep counting by 64ths, and we get to this point, and we are still in denormalized mode because my exponent bits are all zeros. And this is the largest value that is denormalized. Largest denormalized value I can represent. And this would be 0.1111, which is 15/64ths, times 2 to the negative 2, okay? The exponent in denormalized mode. And we'll get 15/64ths times 1/4. This is 15/16ths times 1/4 is 15/64ths. Okay, so this is the largest denormalized value I can represent. And so what is the next value that's going to become? Okay, so the next value, these will all roll over to 0, kind of like an odometer. You can think of this as like 9999, but it's just 1111. And what happens when you roll this over? Well, this becomes a 1. And now we are going to be in normalized mode because now my exponent is not all zeros. I'm at 0, 0, 1. So now that I'm in normalized mode, my exponent bias becomes its regular size of 3. Okay, the exponent bias becomes 3. And so now my exponent is 1 minus 3. My exponent is still negative 2, and I'm still at 2 to the negative 2. Here, with this being 0, 0, 0, 0, and my leading digit is 1, this is kind of normalized mode. I'm going to have 1.000 times 2 to the negative 2, and this is 1/4. 1/4. 1 times 2 to the negative 2 is 1/4, or equivalently 16/64ths. So we've still incremented from 15/64ths to 16/64ths, or 1/4. And maybe this will also help you realize why we needed to change the bias when we were in denormalized mode. And that's because if I had kept it at 2 to the negative 3, this would have been 15/128ths. If I didn't alter the bias and I just left this as 2 to the negative 3, I would have 15/128ths. And then when I jump up to normalized mode, I would go from 15/128ths to 16/64ths, or 1/4, and there would be kind of a huge jump. Because two things are going on. I've changed my exponent from 2 to the negative 3 to 2 to the negative 2, but I've also changed from leading digit 0 to leading digit 1. And that would cause kind of a discontinuity in the number system. So here, we've incremented to 16/64ths. What's the next number? Okay, the next number, this last digit becomes a 1. Exponent bits are still 0, 0, 1. Exponent is still negative 2. The mantissa bits are 0001, so this becomes 1.0001. And this is 1 plus 1/16, or 17/16, times 2 to the negative 2. This is 17/64. So I'm still counting up from 16/64 to 17/64. And we keep going, and we go 18/64, 19/64, 20/64, and we keep going. And we're going to keep going until basically these all fill out with 1s. Okay, so I'm going to have 0001. My exponent is 001. And my mantissa bits are 1111. And what is this? This is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 times 2 to the negative 2. That's 1 plus 15/16 times 1/4, and that becomes 31/64. So this is the largest number I can have where my exponent is 001. All right, and so what happened? What's the next number? It's kind of like rolling the odometer. These are all going to roll over to 0, and this one will change to a 1. So now I'm at 001. These are all zeros. And so what is this? The exponent bits are now 010, which represents 2. We have a bias of 3. My exponent is 2 to the negative 1. Oh, I've forgotten. Have I given you any view quiz answers yet? Okay, first view quiz answer is A. A as in apple. A as in apple is your first view quiz answer. So we have the exponent is 2 minus 3, negative 1. Okay? And the mantissa bits are all 0. So we're going to have 1.0000 times 2 to the negative 1, which is basically just 1/2. Okay, so I've got 1 times 2 to the negative 1, I got 1/2. Or equivalently, that's 32/64. Okay, so we went from 31/64 to 32/64. Okay, what's the next number going to be, though? The next number, I'm going to roll this up. This number is going to become a 1. The last digit here, this becomes a 1. Okay, so what number does that represent? Okay, this number is going to represent 1732. Let's see what happens. Okay, so I got 1.0001 times my exponent is now 2 to the negative 1. Okay, so I have 1 plus 1/16, 17/16, and I'm going to multiply this by 2 to the negative 1, or 1/2. Okay, so this becomes 17/32. It's not, I didn't go from 32/64 to 33/64. I went from 32/64 to 34/64. Okay, and so my increment now is 1/32. It is not possible. I cannot represent 33/64. Okay, this is 32/64, or 1/2. This is 1732s, or 34/64. There's no way for me to represent 33/64, because at this point, when I increment, the numbers increment by 1/32. 1 over 32. All right, and so now, and then what's the next number? Okay, well, oops, here I go from 0. This becomes 10, and this becomes 18/32, right? So I have 1 plus 1/8 times 2 to the negative 1. This becomes 9/16, or 18/32. The increment is 1/32, so we go from 18/32 to 19/32 to 20 over 32, 21, 22 over 32, and we keep going until all of my mantissa bits fill out to be 1. Okay, my mantissa bits all fill out to be 1, and this is 31/32, 31 over 32. All right, and then what's the next value? The next value is 32/32, or 1. Okay, so my exponent bits are 011. The exponent bits are 011, which is 3. With a bias of 3, the exponent is 0. The mantissa bits are all 0, so this becomes 1.0000 times 2 to the 0, or 1, and I just get 1, 32 over 32. Okay. The next number, so now I'm flipping over the page on your handout. We're going to increment this last number to a 1, okay? And now we're kind of in this state where, well, this is 4 bits behind the binary point. So 4 bits behind the binary point is 1/16. And so now I have 1 plus 1/16, there's 17/16. Okay? Times 2 to the 0 times 1. So this is 17/16. And now our step size is now 1/16. Okay? So this is 17, 16, 16, 17, 16, 18, 16, 19, 16. And we keep counting, going up until all of these mantissa bits have filled out with 1, and that would be 31/16. Okay? So our step size started off being 1/64, then they became 1/32. Now they're 1/16. Okay. All right, what's the next number? 31 over 16 is almost 2. So the next number is going to be 2. Okay? So all of these 1s will roll over, and we get 1,000, right? So it's kind of like the odometer again. These roll over to 0, and we increment this to a 1, and this is now 2. And what is the step size here? They're now 1/8, okay? Our step size has gotten bigger to be 1/8. And so this becomes 16/8, 17/8, 18/8, 19/8, and it goes all the way up until we're at 31/8. And then the next value is going to be 32/8, or 4, okay? And then at 32/8, so we have 16/4, 17/4, 18/4, 19/4, and it keeps going at 1 up until we get to 31/4, which is almost 8. That's 7 3/4. And then the next value becomes 4, okay? And our step size is now 1/2. So we have 8, 16 halves, 8 1/2, 17 halves, 18 halves, 19 halves. We get up to 31 halves. Okay? And this is the largest value I can represent. The largest value I can represent with this miniature floating point system, because the next value after this becomes 0, 1, 1, 1, 0, 0, 0. Okay? And what is this? This, when I have all 1s in the exponent and all 0s in the mantissa, this means infinity, right? And that's a little bit strange, because the largest number I can represent being 15.5, that's very, very, very small compared to infinity, okay? But really, even with 64 bits, you know, the largest number you can represent is something on the order of 10 to the 308 or something, and that's a far cry from infinity. It's a big number, and most of our calculations don't have to worry about numbers that big, but that's that falls short of infinity. And so we run into this thing where, the largest number I can represent is 15.5, 31 halves. And at this point, my step size is 1/2. So if you look at the number line, this is what the number line. In the beginning, our step size is 64ths. Then our step size increases to 32nds. Then they get bigger to 1/16. They get bigger to 1/8. They get bigger to 1/4, and then they're 1/2 until we reach 15.5, and anything after that is infinity. And it's interesting, you cannot represent, say, 8 plus 1/4, all right? Over here, we had no problem representing 1/4, 3/4, 2 1/4, things like that. We have no problem representing that. But if you wanted to represent 8.25, it's not possible. Okay? With this miniature floating point system, we cannot represent 8.25. If we try to represent 8.25, it's going to either get turned into 8 or 8.5 if we try to store that number. Okay? You can't represent 8 1/4. Okay? You can't represent 9 1/4 or 8 3/4. Okay? Or 8 1/64. Okay? We can do 64ths here, but if I try to do 1 1/64 or 1 1/32, I can't do it. Okay? Between 1, the next value between 1 and the next value is 1/16. I can go from 1 to 17/16, but I can't do anything smaller than adding a 16th to a 1. Okay? Because if you look at what we have, right, to go from 1 to the next number, I can increment this by 1, and so I'm adding 1/16. If I wanted to have a 32nd, I would require an extra position, an extra bit to store that last number. Okay. And And again, if you think back to kind of this old school calculator, something similar happens, right? If you're dealing with some number like 1, okay, you can have 1.000001, okay? I have 8 digits on my calculator. I can go as small as 1.000001, right? I can have 6 zeros, 1, the decimal point, 6 zeros, and a 1. Okay? I can add 10 to the negative 7 to 1. Okay? But what if I had 100? Okay? Can I add 10 to the negative 7 to 100? I cannot. Or even if I have 10. Okay? So I can add 10 to the negative 1, or 10 to the negative 7 to 9, but if I tried to add 10 to the negative 7 to 10, I can't do it. The smallest I can add would be 10 to the negative 6, because I would have 10 point, and I only have 8 digits total on my screen. I can only do 5 zeros and a 1, right? So at that point, I can only do that. And something similar is going on here, except it's in binary. Right? Okay, so what does this mean? Let me give you your second view quiz answer. Today's second view quiz answer is C. C as in cat. C as in cat. So let's explore double precision floating point numbers a little bit more closely. Again, we have 1 bit for the sign, 11 bits for the exponent, which has a bias of 1023. In denormalized mode, it's a bias of 1022. And we have 52 bits for the mantissa. So 0 would be all zeros, no problem. The smallest non-zero value is 0.00000, 51 zeros, and a 1. So that's basically 2 to the negative 52. Times the smallest possible exponent would be 2 to the negative 1022. That's denormalized mode. And so that becomes 2 to the negative 1074. This is the smallest number I can represent on the computer. 2 to the negative 1074. You can punch it in. The computer is able to produce this, and it says it's 4.94 times 10 to the negative 324. It's a very small number. If you ask for anything smaller, if you try to take this number and divide by 2, or if you try to do 2 to the negative 1075, the computer says, I can't store this. And it just shows it's 0. Okay, anything smaller than this is going to be 0. Okay, the smallest value that is normalized will have an exponent of all zeros and a 1. So not all zeros in the exponent, but all zeros and a 1. Okay, we would have the regular bias of 1023. Our exponent will still be negative 1022. So we're going to still have 2 to the negative 1022. Our mantissa is going to be all zeros, but we're assuming we have a leading 1. So this is going to be 1 times 2 to the negative 1022. And this is the smallest normalized value. This is known as double xmin. So on your computer, you can ask .machine, and what is the smallest value we can represent? That's on the order of 2 times 10 to the negative 308. Okay, that's the smallest normalized value. Not the smallest value possible. Smallest value possible is 2 to the negative 1074, but the smallest normalized value is 2 to the negative 1022. What is the second smallest normalized value I can represent? Okay, well here I will have a bias of 1022 still, but my mantissa will be 1 point, all zeros followed by a 1. So that's basically 1 plus 2 to the negative 52. Okay, so here I can have x is 2, the smallest normalized value is 2 to the negative 1022. That's going to be x. And I can add 2 to the negative 52. I can do 1 plus this times 2 to the negative 1022. Okay? And these two numbers look very similar. We call this y, but this is distinct. This is stored as 0.000001. And we can see this last number has changed from 0.014 to 019. Okay? So that has changed, and it's stored as this. And this difference of adding 2 to the negative 52, this quantity is known as machine epsilon. It's the smallest value you can add to 1, and the computer will recognize that it is distinct from 1. So here, this is 2 to the negative 52, because I have 52 bits in the mantissa, that's the smallest value I can store that is going to distinguish one number from another. So that's machine epsilon. 2.2 times 10 to the negative 16. So that's why we often say the computer has around 16 decimal places of precision, is because 2 to the negative 52 is on the order of 10 to the negative 16. Okay? And so here you can ask, what is the computer? Here's 1. X is 1. Y is 1 plus 2 to the negative 52. And we can ask, is X equal to Y? And the computer says, no, they are different, because the computer recognizes these two values as distinct. Okay. Now here I have the options of printing out all of these digits, and so you can see the difference here. A lot of times though, on Monday I showed you some examples where it was like 0.3, and is that equal to 0.1 plus 0.2? What's happening is that you've got this thing that's on the order of 2 to the negative 52, that's a difference between them, and so the computer thinks that they're different, but they shouldn't be, okay? If you try to add anything smaller than 2 to the negative 52 to 1, the computer can't do it. The computer can't do it. So here I've got 1, and I'm trying to add 2 to the negative 53. The computer can't do it, okay? Now, the computer has no problem representing 2 to the negative 53 by itself. It can represent 2 to the negative 1022 by itself, no problem. But if you think about 1, and you think about how many places after it, right? If you're trying to change that last spot in the bits sequence, it can't add 2 to the negative 53. So if you say A is 1, and we're going to set B equal to 1 plus 2 to the negative 53, we can ask, is A equal to B? And the computer comes back and says, this is true. A is equal to B, even though I try to add 2 to the negative 53 to it, okay? And again, here's what's going on. When we look at 1 stored in the computer, it's stored as this. The bias is 1023, and so the exponent has to be 1023, which is 0, 1, 1, 1, 1, 1, 1, 1, 1, and all zeros in the mantissa. This is equal to 1. Okay? 1 plus machine epsilon is everything's exactly the same, except we've just changed this last bit from a 0 to a 1. And this would be 1 plus 2 to the negative 52. And maybe this reveals why we can't add 2 to the negative 53, because 2 to the negative 53 would require that I have a position right here. And I don't have a position right there. I'm limited to 64 bits total. So here, the smallest thing I can add is the one here, which is 2 to the negative 52. I can't add 2 to the negative 53. Okay. I need to give you more view quiz answers, right? Let me go ahead and give you your second view quiz answer. I already did that? Yeah. I already did that, okay. Okay, your third view quiz answer then will be the letter D. D as in dog. D as in dog will be your third view quiz answer. I can't remember when I'm talking about these things. Okay, third view quiz answer is D. D as in dog. Okay, so think about this. What if you start with x equal to 0? This is a floating point number. And then we're going to run this infinite loop, while true. And we say x is x plus 1. Okay? And so you just start it, you leave your computer, you walk away for, let's say, 10 years, and you come back. Your computer is, we'll say, is fairly fast, and it's been counting. So it goes 1, 2, 3, 4, 5, 6, and it keeps going. And it does this for years. And you come back, and you ask, what is x? You say, stop what you're doing. You come back 10 years later, you say, what is x? What is the computer going to say x is? What's that? It's going to get stuck at 2 to the 53. It's not going to reach in quote-unquote infinity. It's not even going to reach the biggest number, machine double xmax. The biggest number it will reach, it'll get stuck at 2 to the 53. Okay? And why is that? Well, here's just to show. Okay, so this number is very close to 2 to the 53. This is 2 to the 53 over here. So if you type in 900-7199254-740-990, okay, we call that x. We can do x plus 1, and it increments from 990 to 991. We could say add 1 to that, and it goes from 991 to 992. And then I say add 1 to that. And it says it's 992, right? It couldn't add 1 to this number. This is 2 to the 53, and I'm trying to add 1 to it, and it can't do it, okay? At this point, the way the exponents are, the step size is now 2, okay? So I can add 2 to this. I can say add 2 to this, and it goes from 992 to 994. But if I try to add 1, it can't do it. And in fact, your computer has no way, using double precision floating point, it is not possible to represent this number ending with a 3. 9007-199-254-7400-0993 cannot be stored in your computer, okay? Because, again, if you think about the bits being used, one is going to have, basically we have the exponents where this is now 2 to the 53, and this is the 0, so that's the 992, and this is the case where we have 994, okay? But to represent a 993, I would need to have basically another bit somewhere in there. I can't increment it something else, okay? So I can end up with 992, I can end up with 994 because my increment size is now 2, so I can go from 994 to 996 and stuff like that, but I cannot add 1. It gets stuck. And that's a weird thing. It feels weird, but just the way we're storing the numbers, we just don't have a way to represent the number ending in 993 in terms of in binary bits using 64 bits. Okay? Does that kind of make sense, what's going on? The step size at this point has gotten to the size of 2, so you can't increment by 1 anymore. All right, so you can keep filling it out, and this is the largest possible number that you can represent at all, okay? This is all 1s except for the last digit is 0 in the exponent, because all 1s is infinity or not a number. So we have all 1s and a 0 in the exponent. So that becomes exponent of 1023. And then the mantissa is all 1s. We filled this all out. This is as big as we can possibly get. So that's 1 plus 1/2 plus 1/4 plus 1/8 all the way to 2 to the negative 52. Okay, and this becomes 1.797 times 10 to the 308. Okay, and this quantity is known as machine double xmax. This is the largest number we can represent using double precision floating point. We can't represent anything bigger than that. At this point, your increment size is 2 to the 970. 2 to the 970. It's this huge number, okay? And if you try to add anything smaller than 2 to the 970, the computer is not able to add that to this number, which sounds crazy, right? Because the computer can obviously represent 2 to the 970 or 2 to the 969, no problem. But here, if I say A is this number, which is basically machine double x max, and if I say X is A plus 2 to the 969, the computer says A and X are exactly equal to each other, okay? Which seems silly because I'm adding 2 to the 969, a very, very, very big number. But at this point, the double precision can't store anything more precise than this. And so it says this value and this value are exactly the same. If I try to add 2 to the 970 to it, that blows up, and it says it's now infinity. Okay? If you try to add anything to this, you add 2 to the 970 to this, it blows up and it says it's infinity. Okay? So what do we do? Okay? Well, one of the issues we encountered was we saw, if I did 0.1 plus 0.2, is that equal to 0.3? It comes back and it says it's not. So there's some kind of workaround solutions. This function for all dot equal, will say, are they nearly equal? And they say, yeah, 0.1 plus 0.2 as it's stored is nearly equal to 0.3. Okay. This has a few kind of side effects which may or may not be desirable. So here I have A is 1, B is 1 plus 2 to the negative 52. Okay. if I say is A equal to B, the computer says, no, I can tell the difference between these two things. These are not the same number, okay? But if we do all dot equal, are they approximately equal? That's going to come back and say it's true, okay? And all equal, its default behavior is to say 2 to the negative 26. Any value that's any difference smaller than 2 to the negative 26, or around the, the square root of 2 to the negative 52, something around there. Anything smaller than that is going to be seen as equal. So if you do 1 plus 2 to the negative 26, these two values are seen as equal. So 1 versus 1.00000001, that's going to be equal. But if you add 2 to the negative 25, 2 to the negative 25, and you do this, the all equal will come back and say, no, these two values are different. These two values are different. So that's kind of how all equal works. And that's what we have there. Okay, there's another issue called catastrophic cancellation. We won't get into it, but basically, if you can only represent things approximately, whenever you take a difference, you can end up magnifying the approximations, right? So there you could have a piece of wood 254.5 centimeters long, and another piece of wood 253.4 centimeters long. And if you could only measure to the nearest centimeter, you would say this is 255 and the other one's 253. Okay? And the difference between 254.5 and 255 is not that big of a difference. It's 0.2 of a percentage point. Okay? 0.2% off if you take the difference between the actual and the estimated value. Okay? But if you take the difference between these estimates, 255 and 253, that difference would say 2 centimeters, although the actual difference would be 254.5 minus 253.4 would be a difference of 1.1 centimeters. So the error between 2 centimeters and 1.1 centimeters is now huge. That's like an 82% error. Okay? And this is known as catastrophic cancellation. Anytime you take differences between approximate numbers, they get blown up. And so the difference between, again, this number here, 1.00001 on the computer, it cannot be represented exactly. When it's stored in the computer, it's represented as basically 1 plus 5 times 2 to the negative 52, which is this number, which is pretty close to this, okay? It's the difference is on the order of 10 to the negative 16. And then 1.0002 can't be stored exactly. It's represented as this, 1 plus 9 times 2 to the negative 52. The relative error is on the order of 10 to the negative 16. But if you take the difference between these two things, that difference is now going to be computed as exactly 4 times 2 to the negative 52. And that's quite a bit off. Its error is around 10% versus, 10 to the negative 16. So these kind of issues. So, what do we do? Just avoid subtraction, but that's not always a good answer. So, but it's just something you have to be aware of here. Okay, anyway, we'll end here. Have a good weekend, everybody. And we will see you guys on Monday.